And when electron moves or due to their change in position or due to their movement, we got magnetic field. So that is the magnetic field because of electrons movement. But if we place a permanent magnet, so that magnet also have its own magnetic field. So now we have two types of magnetic field interacting with each other. And last time we also observed questions related to that when we have two wires. So when current passes through both wires or both conductors, so their magnetic field interact with each other, right? So in the same scenario, let's suppose if we consider a conductor and we place that conductor in a magnetic field, right? Like one side we have north pole, other side we have south pole, and we place conductor in the middle of them. So let's see what happens in this scenario. So force on a current carrying conductor. In a magnetic field. So this is the topic. So before writing down, if we consider a magnetic field, so for example, we have magnetic poles. So let's suppose this is the north pole of the magnet, and on the other side, we have a south pole. So these are the two poles of the magnets that we are using. And now if we place a conductor in the middle of these magnetic field lines, so let's suppose this is the conductor and the direction of current is like into the paper. This is the direction of current. So direction of magnetic field is always from north to south pole because we already discussed that magnetic field always flows from north to south pole, and the direction of the electric current through the wire is given, that is into the paper. This is the magnetic field lines from north to south. So this is the scenario. Now we have magnetic field, and in this magnetic field we place a conductor, and in that conductor current is also passing through. Right now we are not like taking away from each other. We place the conductor between the magnetic field lines of external magnet. So in this scenario, what happens? As it is mentioned, force on a current carrying conductor. So when we place any current carrying conductor in the uniform magnetic field, so you will get force on the current carrying conductor or force on the wire that we placed in the magnetic field. So it depends upon the orientation of the magnetic field, the orientation and the direction of electric current. So according to that, you will get the direction of force on the conductor. Okay. So first of all, if we explain this whole idea, so due to interaction of magnetic fields of conductor and permanent magnet, a force is produced on the conductor which acts perpendicular to the direction of current and magnetic field. So basically, now we have 3D orientation basically, because magnetic field is on x-axis from left to right. So magnetic field lines are on x-axis. And if we consider electric current, so electric current is going into the paper. So that electric current is on like z-axis into the paper, out of the paper. Now, the vertical orientation is blank. So definitely the force acts on the wire. Either that force will be in upward direction or either it will be in downward direction. So in any one direction, it is possible. And according to the description we mentioned, it is also written the same, which acts perpendicular to the direction of current and magnetic field. So all three quantities are mutually perpendicular to each other. Okay. So this is the concept of force on a current carrying conductor. Let's suppose in this case, the direction of the force is downward. So this is the direction of the force on the wire, that is in downward direction. Secondly, if we want to find out this direction of the force, because we don't know how to identify this direction and we are not doing practical experiments, so there is one easy way to find out the direction of the force or the direction of any unknown quantity given in this scenario with the help of Fleming's left hand rule. Fleming's left hand rule. So basically, when we have to use this Fleming's left hand rule, first of all, as we observe that the direction of magnetic field is given, direction of electric current is given. So to find out the direction of the force, we can use Fleming's left hand rule. So we use Fleming's left hand rule when known quantities, unknown quantities. So let's suppose if you already know about magnetic field and electric current. So if you know about these things, so then you can apply Fleming's left hand rule when force on conductor is unknown. So to find out this force on conductor, we have to use Fleming's left hand rule, right? So in any situation, if we have to find out the direction of the force and the direction of force is not given, so we can use Fleming's left hand rule. Now, how to use this Fleming's left hand rule? So for that, if you consider the orientation, okay. So this is the orientation of Fleming's left hand rule. In this left hand rule, you have to use the orientation of first and second finger and the thumb in this format. You can see thumb is in vertical upward direction, and that represents the force or the motion of the wire or the conductor. And the first finger represents the magnetic field, and the second finger represents the direction of electric current. And you can see that all are at 90-degree compared to each other. So all three quantities are mutually perpendicular to each other. So you always need to keep your fingers and thumb in this position, just like the right hand grip rule we discussed. So for Fleming's left hand rule, we always need to keep things like this to identify the direction of unknown force with the help of Fleming's left hand rule, right? So this is your orientation. Now, for example, if you apply this orientation on this diagram, let's suppose this force is not given. Only these two quantities and the direction of these two quantities are given. Magnetic field is from left to right and electric current is into the paper. So if you apply Fleming's left hand rule with this orientation, so first of all, magnetic field is from left to right. So first finger, so the orientation of first finger is correct, left to right. Okay. Now electric current is into the paper. So this second finger is basically out of the paper. So you have to rotate or you have to like change the direction of electric current that should be into the paper. So you have to rotate your left hand and your first finger pointing towards right hand side and your second finger pointing into the paper like towards the screen. So what is the direction of the thumb you are getting from left hand rule? If you apply Fleming's left hand rule, I will share the orientation also, so that will be easy for you to understand. because you have to perform this left hand rule concept, otherwise you are not able to identify the direction correctly, because there is no formula, there is no calculation for Fleming's left hand rule. So this is the only way to identify the direction. So I shared the picture for the orientation in the group. So for this specific diagram that we draw in the start of the topic, so for this diagram you can see from left hand your first finger is pointing towards right, and your second finger is pointing in the direction of electric current into the paper, and the direction of thumb is downward. So that's why the direction of the force is downward on this conductor, right? Any confusion in this?
Mm.
So this is the pattern of left hand rule. And all the time, if in MCQs they ask you like this, so you have to use the left hand rule to find out the unknown direction. Otherwise, we are not able to solve without using the Fleming's left hand rule. Okay. Next we got orientation of Fleming's left hand rule. And if we talk about the thumb, so thumb represents force on conductor. Secondly, first finger, magnetic field, and second finger for electric current. So this is the concept of Fleming's left hand rule. And again, to make it simple, because definitely we have to draw on the paper and sometimes we have to identify from the given diagrams. So we have to make a simple diagram, and let's see how to make on a simple paper to identify the proper direction, because in this diagram we can identify direction properly, but just like the last time we discussed the concept of into the paper and out of the paper. So let's suppose if we have magnetic poles, this is one magnetic pole, this is the second magnetic pole, north and south. And let's suppose a conductor is placed in the middle, and this shows you the direction of electric current. So this cross shows you that current is moving into the paper. So current is moving into the paper, and again magnetic field lines are from left to right, like this. So this is the direction of magnetic field lines. So in this way, we can also identify the direction of the force, because in this scenario, magnetic field line is passing from left to right, and the direction of current is into the paper. So the direction of current is into the paper. Now, what will be the direction of the force on the conductor in this diagram? So direction of force will be, if you again use left hand rule, so magnetic field lines are moving towards right hand side, just like this, and electric current is into the paper. So again you have to move this orientation of the current into the paper, just like I shared in the group. So again you will get the direction of the force in downward direction. This is the direction of the force, right? So it depends upon the diagram, like in which form the diagram is given. So you have to use the left hand rule in the same pattern all the time, whatever the orientation of the diagram is given. Okay. And one more thing, because we have a current carrying conductor. So as we discussed already, that because of the movement of the electron, magnetic field generates around a conductor or coil. So one magnetic field is because of the conductor, and the other magnetic field is because of the permanent magnet. So there are two magnetic fields, and we are talking about only one force. We are talking about only one force, that is the force on conductor. But last time, if you remember, when we discussed that two conductors are placed close together, so they both exert force on each other. So in this case also, because magnets are permanent, conductor is like free to move. So magnets are not free to move, conductor is free to move. That's why we are only able to observe force on the conductor. But according to Newton's third law, this conductor also exerts force on the magnet, right? But that is not our main subject to calculate or to find out that direction. But just for the basic idea, force is also experienced by magnet, which is equal in magnitude but opposite in direction. So this is the scenario. But again, we are not talking about the movement of the magnet, so that is not our main subject. But still, we have to remember that there will be an opposite force on the magnets also because of the conductor. So in this way, we can identify the direction of force by using Fleming's left hand rule. Okay. And by using this idea, we can apply this concept on DC motor. DC motor means the simple motor that we use in the toy car, etc. So you observe that there are two connection of that motor. We connect one terminal with positive, other with negative, and motor starts to rotate. So that rotation also causes because of this concept of Fleming's left hand rule, right? So let's see how it works. DC motor. So again, we consider the magnetic poles first. So let's suppose this is the north pole again on left hand side, and it is not compulsory to always place north pole on left hand side. You can also place on right hand side. It's your choice. It is not compulsory. So this is the north pole, and in the same way, we have south pole in the opposite direction. So this is the south pole. Now, basically in the motor, we have a proper coil. Now we are not using one single wire, we are using a coil. So let's suppose we have to place a coil in the middle. So this is the coil. And these are two connections that we were talking about. We have positive and negative terminals. So these are two connections that is going to be connected with the power supply. But before that, we have some other things also. We have a ring setup. So these wire are connected with this type of ring. And then on the sides of the ring, we have another component called carbon brushes. So these are carbon brushes, and these carbon brushes are connected with the battery. So this is the whole setup. And if I show you this setup in the proper diagram, because this is on the paper only, but if we consider a little bit 3D diagram that is given in the books also. Okay, this is the diagram basically. So you can see there is a ring, sorry, there is a coil, and that coil is connected with this ring, and this ring actually rotates. And you can see these blue boxes around the ring that is called brush. So with that brush, wire is connected. Because if wire is connected with the coil, so wire starts to round on the coil. So then it will be difficult for the motor to rotate. So that's why we use this carbon brush, because carbon brush provides contact with the power source to the coil. So in this way, we actually use the concept of DC motor, right? Now in this diagram, you can see the name of the components are already given. North pole, south pole, armature, brush, commutator, segment. So that ring is actually called commutator. And if we talk about the concept of this DC motor, like how it works and how it rotates. So first let's see the working, and then we will write the description with it. So basically, again, you already know about the direction of magnetic field. Magnetic field always flows from left to right, like north to south. So this is the direction of the magnetic field. Now, to identify the force, let's consider only one side of the coil first. If you consider this coil, so there is an axle in the middle, just like the fan, like this. So now if you only consider one side, let's suppose A, B, C, D. And for example, we are only talking about side AB, right? So if we are talking about side AB, so now we just focus on AB side, we just ignore D and C side. So according to the direction of current, you can see positive terminal is on left hand side. So current starts to move from this direction. This is the direction of current, and the direction of current is again into the paper, right? From left hand side. So if we consider side AB, so inside AB the direction of current is into the paper, and if we talk about the magnetic field and the direction of the force. So for electric current, it is into the paper, and for the field, magnetic field is from left to right, and for the direction of the force, again, Fleming's left hand rule. If you apply Fleming's left hand rule, so it will be again in downward direction, just like the same scenario we discussed over here, right? So direction of force is downward. So it means that from left hand side, or on the left side of the coil, force acts in downward direction. And what about side CD? If you consider side CD, so in side CD we have only one change, the direction of current. If we consider side CD of the coil, so the direction of current, field, and force. So the direction of current is out of the paper because now current is moving in this direction. So that is out of the paper. And the direction of field is again same,
Yes.
left to right. And because of change in direction of current, if only one quantity changes, so the direction of force also changes. So this is this type of orientation. Magnetic field towards right, current is out of the paper, force upward. So force acts in upward direction. So now you can see it is like a steering wheel. One side is going down, other side is going up. So it starts to rotate, right? So any confusion in this? So this is the process of DC motor, and in this way the motor actually works because of electric current and because of the magnetic field lines, right? Because one side is going upward, other side is going downward, so this will give you the proper orientation or rotation of the motor. And if we talk about the name of the components, so we have permanent magnet, then we have battery, and these blue markers are carbon brushes, and this gray color shows you that ring, this ring, commutator. You can also call it split ring because there is a gap between them, so that's why split ring. Split ring commutators. And this green color is actually a coil of wire. So this is the concept of the DC motor. So the concept of DC motor is very simple because you need to just apply the copy paste idea of it. You don't need to like do anything special in this because it is the normal process, and we have to just know about this process, how it actually works. So if you talk about the working principle, so if we talk about working principle, so it is a force on a current carrying conductor when placed normal to the magnetic field. So this is the concept of working principle. And the second thing is about the components. Okay, in components, basically, we know about the permanent magnet. Permanent magnet creates a strong magnetic field from left to right, and battery provides electric current. So these are very basic things. We already know about them. But if we talk about a split ring commutator, this is the new component. We don't know about it. A split ring commutators. So the purpose of this split ring commutators is they flip the direction of current in the coil when coil crosses the vertical position. And the second thing is carbon brushes. Carbon brushes is a new component because coil, magnet, electric current, or battery, we already know about them. Carbon brushes. So they are made up of graphite, which is soft, and conducts electricity, and also they reduce friction. and provide a base for the rings to rotate on. So this is the information of the components we are using in the DC motor, right? So this is the whole scenario of DC motor, and this DC motor works on the same phenomena as we discussed for the current carrying conductor in a uniform magnetic field. And we also observe that how the direction of current and when the direction of current changes, so how the direction of the force also changes. So this is the pattern of the DC motor that works on the Fleming's left hand rule concept, right?